Good morning, everyone. Teachers, colleagues and colleagues are present here. We welcome you all to the seventh week of ARD Audit Research Methodology Workshop. The topic of today is overview of basic research statistics, a practical approach, which is going to be taken by our own Associate Professor of Public Health in person of Dr. Habibullah Adamu, who is here with us. Thank you so much for joining. Thank you, sir, for sacrificing to take us through this very important topic. Thank you so much. Please help me in welcoming the Associate Professor, Dr. Habibullah Adamu, to give us this important lecture. Highly welcome, sir.
Dr. Muchaba, I think he's back online. I just saw
Dr.
him now.
Habibullah Adamu is now, sir. Yes, I see him. Hello, sir.
Sorry, I had some challenges with the network, so I had to reconnect again. On now, cool. Please, can you see the slide?
Yes, sir, we can see it.
I'm currently sharing the slide. I don't know if you can see it.
Yes, sir, it's visible now. It's on the slideshow. Yes.
Okay, is it moving?
Yes, sir, it is.
Is the slide moving?
Yes, sir, it's moving.
Okay, all right. I just wanted to confirm. Sorry, we are starting a bit behind schedule. We want to discuss overview of basic research statistics today. All of us here are researchers, biomedical researchers, so there is no way we will not have one thing or two to do with research. So this is the outline of what we are going to discuss today by God's grace. And the aim is to give us an overview of what research is all about, so that during our dissertation writing, or when conducting our research, or when doing data analysis, we will be properly guided on what statistical tests to carry out, and so on and so forth, in order to answer our specific objectives. So the use of quantitative data is a day-to-day occurrence. Not only quantitative, even qualitative data. But at least every day we use number, whether in research or in our day-to-day activity. So its use has become so important, such that which is statistics. It used to be, I think it has wide application virtually in all scientific endeavor. So it is therefore very important for us to have at least basic understanding of what statistic is, the classification and the statistical techniques that we have that we usually come across during our researches. So statistics refers to the field of study that is concerned with collection, collation, organizing, summarizing, and analysis of data. And not only that, it also deals with drawing of inference or conclusion about the data based on an observation that we made either on a part or on the whole of the data. So that means there are two major components of this definition. The first one is the one that, and the procedures for what? Collecting our data, putting our data together, analyzing it, and also interpreting the data. So when you do this, you have carried out statistical technique. But sometimes you might decide to go ahead to also use that information that you have to draw conclusion. So based on this definition, statistics is broadly classified into two. One is descriptive statistics, and the second one is inferential statistics. So this descriptive statistics is the one that is covered by the first component of the definition. It deals with just collection, collation, analysis, and interpretation of data. There is no drawing of conclusion. So when you just collect, you analyze your data and you interpret. Maybe in a class, for example, you collect data from maybe 20 students and you say, oh, or maybe the whole class, if you like, you say, oh, this class, the size is 30, 17 are males, 13 are females. So this is their mean age, this is this is that, and you end it there. You just produce your result. That is descriptive statistics, because all you have done is to describe your findings. So this descriptive statistics is also subclassified: measuring average, trying to find the central location; measures of dispersion, the one that deals with measuring variability between values; and then also presentation of the data. Some consider this also as a form of descriptive statistics, while some consider it just as a method of data visualization. So we are going to briefly look at each of them also. The second classification of statistics is the inferential statistics. So this is the one that deals with drawing conclusion. That means you make observation on a small sample and you generalize to a larger sample. For example, you want to carry out a research on medical students, maybe to determine their opinion or perception of something or attitude toward a new teaching method, and you realize, oh, the student size is more than 1,000 and you don't have the resources. So you can go and pick a sample, maybe a representative sample, let's say maybe 200 medical students across each level, and you conduct your research. You determine their attitude. You realize, oh, generally the attitude is positive. So you can now come and say, okay, the attitude of the medical students is positive towards this new teaching method. So that is generalization, because you did not interview each and every single medical student in the school. You only interviewed a cross-section, which is 200, and that is the sample. And now we are concluding, making statement on the whole student. So that is the making of inference or generalization. We are going to look at it again. So in drawing conclusion, because you did not interview everybody, that means it is possible your conclusion that yes, they have positive attitude. It's possible it is true, and it's possible by the time you interview everybody, if someone decide, oh, me, I have the resources, this 1,500 students, let me interview each and every single person. It is possible that person might see a different thing. Maybe you see that, oh, actually the attitude is even negative. So because whenever you draw conclusion based on small observation, now you are drawing conclusion to a larger picture, it is possible, it is true, or it is not true. So that means inferential statistics deals with what? Probability. It is possible, it is true, your conclusion, it is possible, the conclusion is not true. So please, we should have it at the back of our mind that whenever we deal with inferential statistics, we are dealing with probability. And that probability is the one that is often determined using what is referred to as p-value. I'm sure we are all familiar with this term p-value. We are going to look at it also again, how to apply it in our research. So any research that deals with p-value is an inferential statistics. So it implies whenever we carry out inferential statistics, by default, default setting should know that we must build the p-value and present it. So this question, the answer is high of actual no. So let's look at some basic in statistics. First one is which tell
Welcome back, sir.
Okay, it keeps logging me out. I don't know at what point was I logged out so that I just go straight to that point.
No, it's just now, sir.
Okay, it's just, I think that means it's on this slide.
Yes, sir.
Okay, so that is data. The other one is population. So in statistics, when we say population, it is referred to largest collection of interest. So if you are interested in researching 600 medical students, for example, so all the 600 medical students now become your population. If you are interested in studying the whole students of a school, so that means your study population now becomes all the students of that school. If you are interested in studying children under 5 years in a local government, your population becomes children under 5 years of that particular local government because they are the ones you are interested in studying. So population is often can be either finite or infinite. I think this description is not in the slide. So we can have finite population or infinite population. So technically, a finite population is the population that the actual number is known. So if you know the actual number of population, then it is referred to as a finite population. If the actual number is not known, then that population is regarded as an infinite population. And so, however, in sample size determination, also sometimes there is also another sub uh, another explanation to it. So if as with respect to determining sample size, because there are different formula when the population is so large and when the population is not large. So sometimes if you are dealing with sample size estimation, a finite population is also considered as population that the size is not more than 10,000, while infinite population that is the size is more than 10,000. So this is usually applied as with respect to sample size estimation, but technically finite is the one that you know the actual number, and infinite, the one that you do not know the actual number. Then sample. Sample is a portion of a population or a section of a population. So if you look, if your population of interest, your study population is, for example, medical students of a particular school, so your sample will be cross-section of those students. Maybe you pick representative sample from each school. So that makes your, what is it called? Sample. So usually sample also is considered as there is representative sample and sample that is not representative. So a representative sample is called random sample, meaning that that sample, a sample that is selected in such a way that each member, each member was given equal chance of being selected. Some call it sample that is selected using a probability method. Either you ballot or you follow any of the techniques that are used in obtaining probability sample. So that is a random sample. So as much as possible in research, a random sample is preferred. That means sample that is obtained from probability sampling techniques. So there is also inductive reasoning. Inductive reasoning is a form of inference also. That means drawing of conclusion, whereby you make observation on a small sample and then you draw your conclusion to the population. So you pick cross-section of students from a school, and then you draw conclusion to the whole students in the school. That is inductive reasoning. There is also deductive reasoning, which is the opposite. You make you make your observation on the whole population, and then you draw conclusion to a small sample. So if you are aware, for example, uh, in a state that a particular school, there is a particular school with so type of uniform, you know that all the students in that school either have a particular type of uniform, or you have information that students in a particular school are the only ones that are aware of something, maybe one information, and you come across a student at random and you realize that student has that information. So you conclude that, this student is from that school. So that is deductive reasoning. You have your information on a whole school, and now you are drawing your conclusion to a particular individual or to a sample. That is deductive reasoning. The other one is variable. This is very, very important. You are going to come across it over and over and over. During analysis, it is very, very important also to know the different types of variables. This one is very, very important. So variable can be either independent or dependent. So variable is what? Simply, it's any measurable characteristic that can assume any form. So that is the basic definition of variable. A measurable characteristic that can assume any form. That means it is something that is measurable and something that varies. If you come to a class, you can take the age. The age varies. This one has his own age and so on and so forth. The weight also can vary. It could be the same, but it can also vary. So that makes it a variable. You look at skin color. Skin color also varies from one type of ways to look at to understand what a variable is. So when we talk about dependent or independent variable, a dependent variable, maybe we should start with the dependent variable. A dependent variable is that variable that is value or appearance.
This network logged him out. Let me reach out to him.
I don't know today. I don't know what is happening to the network. Network is terrible. Please, at what point was I lost?
Hello,
Hello?
sir. When you were trying to explain the type of variable, you have finished describing what a variable is. You were going to the types.
Okay. All right.
Yes, sir.
So let me come over again. I said, so since we understand what the variable is, now the types, because they are the ones that are commonly encountered, especially the first, in fact, all the types during analysis, you need to know which one you are dealing with, especially dependent and independent. You need to know which one is dependent and you need to know which one is independent, because dependent usually, in fact, not usually, it goes to the column. If you are doing analysis and you are selecting your variables, there is a place you need to place your dependent and there is a place you need to place your independent variables. So that makes it mandatory for one to understand which one is dependent variable and which one is independent. So dependent variable in its simplest practical form is that variable whose value or outcome is determined by another variable. So if you have two variables, A and B, variable A is the value of variable A, for example, is determined by variable V. So that means variable A is dependent variable. For example, if we take skin color we know can be determined by several factors. One of such factors is genetic factors. So that means the way someone appears as far as skin color is concerned is determined by other factors. Genetic factors, weather condition, nutrition, cosmetic, the type of cosmetic one is using, whether someone is using or not. All this can determine the skin color of someone. So that variable on the source of this problem. Is it from my own end or my end? What do I do? Because this place has normal please, are we together again or I'm still disconnected?
So you are still disconnected.
I think you are the ones disconnected because me, I'm seeing.
Yes, you can see your screen and we can hear you now.
Yes, please.
I think the network today, I don't know. So Please, did you get the explanation of dependent variable and the example?
Yes, sir, we did.
What of independent?
I say dependent, that the outcome is dependent on the
Yes, and I
exposure.
gave example.
Yes, I gave
I
example.
gave
Then you say,
practical example.
yes, about skin color. Then you talk about the dependent goes to the colon. That was where we stopped.
Okay. All right. So the column, because you need to know what the dependent is before you know whether it should go to whether something is a dependent or not. So that's why I use example of skin color. I said skin color, the color of someone's skin is determined by other factors such as weather condition, nutrition, use of cosmetic, and so on. That all of this can determine how someone's skin color, what someone's skin color will look like. So that makes skin color dependent variable. On the other hand, an independent variable is that one that determines the value or outcome of another variable. So if we come back to this skin color again, genetic factors can determine someone's skin color. Use of cosmetic can determine someone's skin color. Nutritional factors can determine someone's skin color, and so on and so forth. So that makes all these independent variables because they are variables that can determine the outcome of other variables. So that is just one example. So all you need to know is if you have two variables, you want to know which one is dependent, which one is independent, just look at, okay, this variable that I'm considering, its value, is it influenced by other factors or by any other factor? If yes, then that makes it dependent. This one, is it influencing the other variables I'm considering? If yes, then that makes it an independent variable. So qualitative versus quantitative variable here is a quantitative variable is considered as that variable that is described using number. Any variable that you describe it, either you collect it or you describe it in numerical terms by using number, then that is a quantitative variable. So for example, age, we describe it using number. Weight is another example. Number of people in a class is still using numerical values. So that means all these are what? Quantitative variables. So quantitative variable can be further classified into discrete or continuous variable. Because this is also important in some analysis, you need to be able to know this one is discrete and this one is continuous. So discrete quantitative variable is that quantitative variable that can only take whole number. If you want to describe it, you have to describe it as whole number. For example, number of people in a class. Of course, it has to be a whole number. We cannot have 5.6 people or so. Number of chairs in a class, number of classrooms. All these are things you can only describe in terms of whole number. So it makes it discrete. So generally frequencies are considered as discrete quantitative variables. Continuous variable is that quantitative variable that can assume any value within a range. That means it can accept fractions or decimal points. For example, weight. Weight can assume any value within a range because it can be 6.34567 whatever milligrams or kg as the case may be. Height can also assume value because it can take decimals. So these are examples of continuous variables. So categorical qualitative variable, on the other hand, is that variable that you cannot describe it using number. You can't describe it in numerical terms. So that makes it, so you can only describe it in terms of its attributes or its characters and so on and so forth. So that is a qualitative variable. For example, sex. You cannot describe one's sex in numerical terms. So it's either a male or a female. So when you say a male, we know the phenotypic appearance of a male. If we say female, the same thing. Skin color, you can't describe it in numerical terms under normal circumstances. But maybe someone in physics can do that. But as far as we know, skin color, you can only say is very dark man, whatever. You just say chocolate color, fair, yellow, black, and so on and so forth. So these are qualitative variables because you can describe them using number. So qualitative variables, sometimes some quantitative variables can be categorized into categories. So when that happens, those categorical variables are also treated as qualitative variables. So that is why sometimes they are used interchangeably because the same principles apply to them during analysis. So when you say categorical variable, you say qualitative variable, they are more or less referring to similar things. It's just that some quantitative variables can be categorized. Maybe age. Age is a continuous variable even, but you can categorize age into less than 20, 20 to 25, and so on and so forth, so that you have it in groups. So in this instance, if you are dealing with it during analysis, you may deal with it as a qualitative variable. So it depends, but basically qualitative variable is that one that you cannot describe in numerical terms, as simple as that. Then we have dichotomous and polychotomous variable. Here is based on the number of categories. So if a variable has only two categories, it's a dichotomous variable. For example, sex is either you are a male or you are a female. Yes or no, present, absent, dead, alive. So all these are only two categories. So sometimes even a variable that has several categories, you may decide to collapse it into having only two categories. That is still dichotomous variable. A polychotomous variable is variable that has more than two categories. For example, ethnicity. So ethnicity in Nigeria, I think, is almost 300 ethnic groups. So religion, level of education, and so on and so forth. All these have different categories. Severity of disease, mild, moderate, severe. All these have categories that are more than two, so they are polychotomous variables. So now that we know some basic um, terms in statistics, let's look at measures of central tendency, because we say they are under descriptive statistical analysis. Under descriptive statistics, we say it includes measures of central tendency, measures of dispersion, and sometimes data summarization and presentation. So these measures of central tendency are measures of what? Average. If you have set of data like age of 10 patients, 20 patients, 30 patients, like that, if it is displayed just like that, row that you have it 13, 16, whatever, and it's presented to you maybe as a doctor, they say, okay, this is the age distribution of the patients we are going to see. When you look at it at a glance, it will not give you any reasonable information. So, but by the time someone picks a single number that summarizes all of them and say, oh, you are going to see 20 patients and their mean age is 11. That is one value summarizing all the other ages of the 20 patients. As soon as you see that, you know that, oh, okay, most of the patients, I'm likely going to be dealing with children. So that is the advantage of measures of central tendency. They try to give you the central location, the central point. If there are ages of 10 patients, they will give you one value that will represent those 10 patients. That one value is the value that occupies the central location. Why are we saying it is one that occupies the central location? Because it is the value that the remaining ages surround. That means some are a bit above that value, while some are a bit below that value. So it is very good in statistics because it gives you overall idea of the type of um, measure that you are dealing with. So the main examples here are the main types here are mean, median, and mode. Mean is the one that is most widely used. It is often also referred to as simply average, and it can be calculated by adding all the sum of the values and dividing it by the number of observations. So if you have 10 observations, that means, for example, you have measured the weight of 10 patients. You want to know the mean, you simply add all of them and divide by 10 because they are 10. If the values are close to each other, if the values are close to each other, that means if it is age, if the ages are close to each other, not widely spaced. So if the values are close to each other, then that is when the data might be regarded as, oh, normally distributed data. So that means mean is only used if the data is normally distributed. If it is not normally distributed, if you use mean, it is going to give you a misleading result. So if a value is a lot smaller or larger than others, mean will not give you a clearer picture of the central location. So these are the examples: geometric mean, harmonic mean, weighted mean, arithmetic mean, and so on and so forth. So but mainly it is the arithmetic mean that we use, especially in most biomedical researches. So median, on the other hand, also measures the average. However, it is mainly applied if the data is not normally distributed. So that means if it is skewed. Data is skewed if there are extreme values inside, meaning that some values are significantly lower than majority of the values or significantly higher than majority of the values. So when that is used, if you decide to use mean in that situation, it is going to give you a misleading result because mean is affected by extreme values, whereas median is not affected by extreme values. For example, if you have, we have here on the screen, represent weight of 5 adults, 54, 55, 56, 58, and 59. The median is 50, and the median is 56. So that means half of the values are above that 56 and half are below that 56. So in practical terms, that is what it means. But if we are to now have, I thought I had included it in this slide, probably is in another slide for something, practical example. But we can also do it so that we appreciate why mean should not be used if the data is skewed. Let's say you have 5 patients. Let's just take example. If you have paper and biro, you can also do it there. Let's say we have 5 patients and their weights are 3, let's say 3, 4, 3, 6, and 5. So if we are to calculate the mean of this, where we have 7, 10, 16, and 20, 21. So that is 21 all over 5. I just want us to appreciate the this difference. So 21 divided by 5 we have is 4.2. So that means the mean age is approximately 4 years. So if you are told you have 5 patients to see and their mean age is 4 years, you know that you are dealing with small children, even preschool children, as the case may be. So it gives you a clear picture. But in this, let's now assume the age distribution is 3, 4, 3, 6, and 100. Let's say the 5th patient is 100 years old. Let's calculate the mean also. 3, 4 here is 7, 10, 16. So 116 divided by 5. That is 23.2. So the mean age here is 23. So if you are told as a doctor that, oh, you have 5 patients to see and their mean age is 23 years, you will think you are dealing with adults because you say mean age 23. Say, then, but by the time you enter, the first patient comes in, he is 3 years old. The second patient, 4 years old. The third, 3 years old. You think, am I at the right place? Why? Because you have been misled. The mean age you use, mean was not supposed to be used in that situation because there is an extreme value in the distribution. That 100 years is significantly larger than the remaining values. So that is why we say mean is affected by extreme values. So once there is extreme value and you use mean, it is likely going to give you a misleading result. Now, why are we saying median should be used if there are extreme values? So let's look at the second example. The median will just be arranged 3, 3, 4, 6, and then 100. We say median is the central value, called the middle one. So the median is what? 4. So if they say the median age of the patients we are going to see is 4 years, that is closer to the actual ages of the patients we are going to see. So even if the first one comes in is 3 years, the second one is 3, the third is 4, you are not going to be surprised because the median gives you the picture that is closer to the reality. So please, before you use mean, always ensure that your data is normally distributed. There is a simple way of knowing if data is normally distributed or not. Once you have your mean and you have your standard deviation, you can just run a simple check. That your standard deviation, just double it, multiply it by 2, and see if you can subtract it from the mean. If you can subtract the mean, if you can subtract it from the mean without having a negative value, then that means that data is fairly normally distributed. For example, if they say the mean age is 20 plus or minus 5, that plus or minus 5 is the standard deviation. So that means if we are to use this formula, we just say, okay, they say we should double the standard deviation. So that means 5 times 2, which is 10. So 20 minus 10, we have 10. So the value is still what? A positive value. So that means in this instance, the age is what? fairly normally distributed. But if they say mean age 20 plus or minus 12, so here the standard deviation is 12. When you double it, it will be what? 24. By the time you say 20, which is the mean, minus 24, which is double the standard deviation, that will be what? Minus 2. So, I mean, minus 4. So that means that age is not normally distributed. So that is a simple check. Once you run your analysis, you have your mean, you have your standard deviation, just do this so that you know whether the mean is giving you a reliable information or not. So mode is just the most commonly appearing, the frequent is not so much used. And so we are not going to, since there is no time even. Then we have measures of dispersion. Measures of dispersion are measures of variation between values. So this variation can come up in different scenarios. For example, if we measure the blood pressure of 10 patients, we can find out that that the value might vary. It's not likely to be the same for all the 10 patients. However, all of them, the value can still be what? Normal. That, oh, the blood pressure is normal. This one is 110 is normal. This one, 115 is normal, and so on and so forth. So now the question is, what is normal variation? It means variation is normal within observation. Since you cannot have every value to be the same, that means it is normal to have variation. So, but then what constitutes normal variation? And how are the variations measured? If we want to measure, for us to know whether variation is normal, we need to be able to what? Measure it and then weigh it against something to know, okay, this one is within normal or not. So the methods and the techniques that are used in measuring variation in statistics is what is referred to as measures of dispersion. And there are different types. We have standard deviation, we have confidence interval, range, interquartile range, variance, coefficient of variations, and so on and so forth. Each of them is used in different scenarios. So we are going to look at application for at least some of them, if not all. So range is simply the difference between the maximum value and the minimum value in a data set. So this one will not dwell so much on it. Variance refers to the average of the squared deviation from the arithmetic mean. So it's also used because it gives us the measure of variations between values. For example, these values that we use in the previous example, the ages of the 5 children, 5 patients, 3, 4, 3, 6, and so on and so forth. So what variance does is to measure the difference between 3 and 4, the difference between 3 and 6, 4 and 6, and so on and so forth. So there is a technique that is used whereby you have to, because all you are doing is what? You are measuring how it varies from the mean. So if the mean is 4 years, because we calculated the mean to be 4.2. So what is the difference? The first value that is 3, what is the difference between it and that mean? The next value, what is the difference between it and the mean? So those that are below the mean, even if they are 20 or 30 in number, you pick each of them and see how far it varies from the mean. Those that are above it also, you pick it and see how far it varies from the mean. So when you do that and you sum everything, so it gives you the variance. So standard deviation is also computed in a similar way, but it gives us a better data, because Standard deviation is just the square root of the variance. If you have your variance, you can, to get your standard deviation, you just get the variance. I mean, you just get the square root. So standard deviation gives us a smaller value that under normal circumstance, we expect it to be what? Lower than the mean value. Because if you use variance, the value is usually large. So if you want to use this method that we just described to know whether it's normally distributed or not, it's not going to be, it's easier to use the standard deviation. So wherever standard deviation is applicable, variance will also be used in that regard. So standard deviation gives you the what? The variation of each value in a data set from what? The mean value. So by the time you add everything, it gives you that. So if you have your mean and your standard deviation, these two gives you the idea of the distribution of your data, because it gives you the central value and it gives you the spread, how each value deviates from the mean value. So that is the importance of these measures. Then we have interquartile range. Interquartile range also, because this shows the distribution of the middle half of a data set. So sometimes when, if you have, in practical terms, it is used if the data is skewed. Remember we say median is used when the distribution is skewed. That is when there are extreme values, either values that are extremely large or extremely small. So in that case, we say if we use mean, it will give us misleading result. And we saw it in the example that we cited. So for the measure of dispersion also, if you have a data that is skewed, please don't use standard deviation. Standard deviation is going to give you a misleading result. Just like mean will give you a misleading result if the data is skewed for measure of central tendency. For measure of dispersion, if your data is skewed, instead of using standard deviation, use interquartile range. So interquartile range goes with median because all of them are not affected by what? Extreme values. So we'll not dwell on the calculation, because here we are more interested in the practical application. So it is applied, you use interquartile range when the data is skewed and you want to know the spread. So since you cannot use standard deviation, you use what is it called? Interquartile range. So mean deviation is also there. This one is not as sensitive as standard deviation. So there are other ones. Coefficient of variation is there. Coefficient of variation is also a measure of dispersion. So you can use it to compare variation if you have two values that are measured in different units. Maybe you want to compare variation between age, between height and weight, which one has higher variation. So that is where you use coefficient of variation, because it will give you the value of it could quantify the variation for each of the variables in percentage. So the one that has the higher percentage is the one that has the higher variation. So coefficient of variation is expressed in percent. So that is overview of descriptive statistics and their application. Inferential statistics, on the other hand, we said they are encountered when we draw conclusion, when we are making inference. We only make small observation, now we are generalizing to a larger group. So that is inferential statistics. And we say usually they involve probability. So that means whenever we do it, we have to be able to quantify the probability of error in what we are. So they are commonly encountered in hypothesis testing, such as t-test, chi-square test, ANOVA, and so on. So whenever we use t-test, we are going to see t-test later. It is expected that we must present the p-value, because it's one that will give us the probability of making that observation in error or due to chance. Whenever we use chi-square test, by default, we must present the p-value. Whenever we use ANOVA, the same thing. We have also correlation and regression, use of confidence interval. We are going to see the application of each of them. So, test of association. Some of these statistical tests are used in testing association. So because variables that coexist together, some are associated with each other while some are not. So if you want to know whether a certain factor is cause of a particular disease, the first thing to do is that you must establish that that suspected factor has association or relationship with the disease. If there is no association, don't bother yourself, just end it there. It cannot be the cause of that particular disease. So test of association is very important in statistics and in research. So there are different ways, different techniques that can be used. And so the choice of the techniques will depend on the variables you are considering, whether they are quantitative variables or qualitative variables. So that is why I said knowledge of variable, understanding what variables are and the types is very, very important. So this is just an example. There are statistical tests you use if your variables are quantitative, and there are some that you use if you are considering qualitative variables. So let's look at some of them. We have correlation. Correlation is used if you are trying to test for association among variables that are quantitative in nature. So if you want to test, is there association? Yes, you can use correlation. For example, you want to test, is there association between body mass index and systolic blood pressure? All of BMI is quantitative, systolic blood pressure is quantitative. So you go ahead and use your what? Correlation. Chi-square test. Chi-square test is also another test that can be used to test for association. However, it is for what? Categorical variables. Variables that are in what? In categories. For example, sex. You want to look at whether there is association between sex and blood pressure. So you can categorize your what? Your blood pressure into normal and hypertensive. And then for your sex is already categorized into male versus female. So here you have your variables in categories. So you cannot use correlation in this situation because your variables have been categorized. So that is where you now use chi-square test. So chi-square test is the one that is commonly used if you have variables that are in categories and you want to test whether there is association between them or not. So you use chi-square test. It is a form of bivariate analysis. So there is also coefficient of association. So if you want variables that are discrete in number, those that are in frequencies, variables that are in frequencies, we describe discrete variables, we say those ones that take only whole number. So if you have variables that are discrete in number and you want to know whether there is association between them, you can use coefficient of association. Relative risk can also be used to test whether there is association or not, especially if you are doing risk factor study. You want to determine risk factors for certain disease. So the first thing to do is to see whether that factor is having even any association with the disease. So it's encountered in studies like cohort studies. Cohort studies are epidemiological studies that deals with effect of exposure to something, whether exposure to a factor can lead to disease in future or not. So you can follow up two groups, maybe one group exposed to the factor you are suspecting, the other group not exposed, and you follow them for a long time, maybe 15 years, 20 years, and at the end of the day, you carry out your analysis. So that analysis you are going to carry out at that time to know whether this factor you are suspecting is a risk factor or not is relative risk. It includes estimating the relative risk. We are going to see the interpretation. Odds ratio, the same thing, you can use it. This one is in case control studies that we use odds ratio. So let's look at chi-square test. So we say chi-square test is often associated with hypothesis testing and is the most frequently used test of association. Rarely will you see an analysis that involves testing of association that will not use chi-square test. However, it should be noted that we say it is for what? Categorical variables. So it measures the difference between observed and expected frequencies. So you do your study, you observe, you collect data on the frequencies of certain, whether a disease condition or whatever you are interested in your study population. So what happens in chi-square test is that your observed data is compared with a hypothetical data. And that is what happens during the analysis if you are running chi-square test analysis. But here we are looking at the practical approach, so we are not going to dwell into how the calculation is done. No, what we are interested in is what? To know when to use the chi-square test, when not to use it, and to be able to interpret the result at the end of the day. So a value, your result will be a value. So
Network fluctuate again. Let me contact him and help him.
thing keeps going on and off.
Yes, sir.
Please, where are we? Where are we now at what? This is the slide. Is this
Slide
the slide
21.
that we call 21, cool?
Yes, sir.
Very good. So that means this slide. So this, let's take an example. This example that is displaying, they say Adamu et al. Reported in their study that patient satisfaction was found to be associated with their duration of waiting time. That so waiting time here long duration, short duration. So if not, under normal circumstances, waiting time is a quantitative variable, is correlation that should go with it. But you know, we say sometimes even quantitative variables can be categorized. So here it was categorized into different categories: long duration, short. This thing is frustrating. Please, are we together?
Yes, sir.
Yes, sir.
So as a general rule, less than 0.05 is considered statistically significant. Please, this one, you should have it at the back
Yes, sir.
of it. Eh? Are we together?
Yes, sir.
So we say, as a general rule, interpreting p-value. Once you have your p-value, all you need to do is look at that value. Is it less than 0.05? If it is less than 0.05, you conclude that what? Your observation is significant. If it is 0.05 or above 0.05, you conclude that, okay, your observation is not significant. So it depends on what your observation is. If your observation is that you are testing for association, and then you see your p-value less than 0.05, then you conclude that what? There is significant association. If you are testing for difference, maybe mean difference, and your p-value is less than 0.05, you conclude there is what? Statistically significant difference. Whatever it is you are trying to test, and your p-value is less than 0.05, your conclusion should be that that thing you are testing is what? Statistically significant. If you are testing for poverty, and your p-value is less than 0.05, it means there is statistically significant poverty. If you are testing for happiness, the p-value is less than 0.05, your conclusion should be what? There is statistically significant happiness, and so on and so forth. But once it's up to 0.05 and above, then you conclude that what? That thing you are testing for or you are looking for is what? Is not statistically significant. So that is just the simple way of using p-value. So the cutoff is 0.05. Below it, you conclude it is what? Statistically significant. Above O equal to that value, you what? Conclude there is no statistically, that it is what? Not statistically significant. There are reasons behind that, but maybe to save time, because this network keeps going on and off, so there may not be reason. So if time permits, maybe we can discuss the reason why we say less than is significant, above or equal to is not significant. So we should note that when we are using chi-square test, please, we should know that there are some consideration, because chi-square test is not used in all situations. So there are some consideration. Where the sample size is too small, chi-square test may not give us valid result. So if you have very small data, Maybe the sample size, you just have 10 respondents. If you use chi-square test, it's not likely to give you valid result. So therefore, because the simplest table that is used for analysis in chi-square test, that is the 2x2 contingency table. There is a table called 2x2 contingency table, which has 4 cells. So it is expected that in each of the cell, the frequency should be at least up to 5. If the frequency is not up to 5, you check among the cells in the cross tabulation table, because if you use computer, whether it's SPSS you use or whichever one, it is going to give you a cross tabulation table. So the values will be distributed. The frequency, you will see the frequency distribution in the cells in the table. So all you need to do is look at each of the cell. Is the frequency up to 5 in each of the cell? Once it's up to 5 in each of the cell, go ahead, use your chi-square test. But if there is a cell or cells even that have values less than 5, then it is not wise to use chi-square test, because the result you are going to get might not be a very valid result. So that is why it is required that the minimum frequency, the minimum sample size that one should have in using chi-square test is at least sample size of 20. Some say sample size of 30, because in statistics, sample size of 30 is one that is regarded as large sample. Anything below it is a small sample. So even if you are doing manual calculation, there are some consideration, but we are not interested for now in the calculation. We are interested in the what? Application. So if you want to use chi-square test, please, our sample size should be at least 20 and above. And when we run the analysis, in the result, we should look at the cross tabulation table that will be displayed. Are the values in each cell up to 5? That is the frequency. If it is not, then there is problem. So good enough, if you are using SPSS, especially below the chi-square table, it will give you the summary that so number, so percent of cells have expected count less than 5. So usually, if once the expected count in all the cells is those ones with less than 5, once it is not more than 25, fine, you can use your chi-square test. So for each analysis, just look at the chi-square table. Maybe we'll look at, if time permits, I will see if I can get some so that we'll use it for the interpretation. I think probably I opened the wrong, because there is another one that has all these explanations so that it can be used directly. So, but the most important thing is know that the frequency in each cell should be at least 5, the sample size should be at least 20, and that not more than 25% of the cells should have expected count less than 5. So that means it is possible to have expected count less than 5 and still chi-square test might still be what? Valid. If the expected count that are less than 5, the cells with expected count less than 5, if they are not more than 25%, then you can still go ahead to use your chi-square test. To overcome this, if you have cells that have counts less than 5, you use Fisher's exact test. So usually when you are running the analysis, if it is using SPSS, if you are running the analysis, you will see that there is a place you select Fisher's exact. So it will give you the person chi-square value and its corresponding p-value, which is the one that is usually used. But if you now see that there are some cells with expected count less than 5 and they are a bit many, then instead of using the p-value for person chi-square, you use the p-value for Fisher's exact test. So that is just, but you run the analysis in the same everything is displayed in the same table. Another way to overcome this also, there is yet continuity correction. This one is not commonly used. So, but the one that you need to know at least is the Pearson chi-square and the Fisher's exact, when to use the Fisher's exact. That is when you have cells with frequencies less than 5. Then you pick the p-value for Fisher's exact. Regression is also another statistical test that we commonly use. Here, it is used for what? Predicting outcomes. You have dependent variable, you have independent variable. So dependent variable is the variable that is usually predicted. For example, you want to predict blood pressure of a group of patients based on their age. As their age increases, what happens to the blood pressure? Or you want to predict their blood pressure based on their BMI. As their BMI begins to change, either by increasing or decreasing, what will be the value of their blood pressure? Will it increase or decrease, and so on and so forth? So if you want to predict in statistics, the right application to use is regression. So regression is the one that is, so if you want to determine predictors, if in your research, one of the objective is to also determine the predictors of so practice, the predictors of certain diseases. So your right application to use is what? Regression. So regression are of various types. We have simple regression, there is multiple regression, and there is logistic regression. So here, the first thing, please, we should note that the main determinant of the type of regression one needs to use is the nature of what? The dependent variable. It is the dependent variable that determines what type of regression you should use, whether it is simple, whether it is multiple, whether it is logistic, and so on and so forth. Please, it is your, if you don't know between the variables you are analyzing, if you don't know which one is the dependent variable, you can't use regression. So that is why I had to take my time to explain the difference between dependent and independent variable. Please always understand it, because it's very, very important. Even if you are using computer, by the time you start running the analysis, it will take you to a place where you just see space dependent, meaning that it is waiting for you to select the dependent variable and put it there. Computer will not tell you which one is dependent. You should know it. So that is the essence of understanding this. So if the dependent variable is a quantitative variable, you use what? You use linear regression. Please, once the dependent variable is a quantitative variable, use linear regression. If the dependent variable is a qualitative variable or categorical variable that has been categorized, use logistic regression. So that means broadly, this regression is either linear regression or logistic regression. Linear regression, if what we are trying to predict is a quantitative variable, for example, if you are predicting blood pressure, if we are predicting fasting blood sugar, if we are predicting weight, all these are quantitative variables. So it means we are going to use linear regression. If we are predicting, for example, outcome of treatment, either cured or not cured, for example, this one is categorical variable. So we use what? Logistic regression. So now within linear regression, we can subclassify it into either simple linear regression or multiple linear regression, which is what we have here on the slide. So we say simple linear regression is when you are predicting one quantitative variable from one independent variable. You are predicting one quantitative variable from what? One independent variable. That independent variable can be either quantitative or qualitative, it doesn't matter. But the most important thing is that that thing you are predicting should be a quantitative variable, because that is when you can use linear regression. So simple regression, you are predicting one quantitative variable from only one independent variable. For example, you are predicting blood pressure based on someone's age. So you are only predicting from age. So that makes it simple linear regression. Multiple regression, for example, is used when you are predicting one quantitative variable from what? More than one independent variable. For example, you are predicting blood pressure based on one's age and smoking status. It can even be more than, you can decide to predict someone's blood pressure based on his age, based on gender, based on level of education, based on income, based on exercise, and so on and so forth. So once the independent variable is more than one, and what you are predicting is quantitative in nature, you use what? Multiple linear regression. Logistic regression. This is used when we are predicting qualitative variable. So for logistic regression also, there are two considerations. If what you are predicting has only two categories, that means if it is dichotomous. Remember when we talked about types of variable, we also describe what dichotomous variable is. We say it's a variable that has only two categories. So if what you are predicting has only two categories, you use what? Binary logistic regression. So in most cases, in most of our research, you see that the outcome, we try to make it a binary outcome because the interpretation is easier. If you want to channel your intervention, it's easier to know where the intervention should go. However, if the categories are more than two, then we use multinomial logistic regression. Some call it polynomial logistic regression. But in most cases, is the binary logistic. So as much as possible, try and make your outcome variable binary in nature. That means a dichotomous. That means only two outcomes. Cured, not cured, and so on and so forth. So that is the application of regression. Now, how do we interpret the results of regression? Because when you run the analysis, it will give, we have seen for chi-square test how to interpret it. We said the most important thing is, let's look at the p-value. Is that p-value significant or not? Is it less than 0.05 or not? So also, this table is for a research that tried to look at the predictors of utilization of family planning. So the example is predicting the utilization of family planning method based on woman's age, marital status, and residence. So these were the three factors that were looked at to see whether any of them could be a predictor of utilization of family planning. So logistic regression uses odds ratio. I don't know. Is that, oh, how come there is no odds ratio here? Maybe it's very important to have description of odds ratio. Maybe I will have to digress a bit. Maybe I have to digress a bit. So just give me like 1 minute. I will share with you a slide that has odds ratio so that before we come back to this, just 1 minute. I know I should have
Okay, sir. Thank you, sir. Okay, sir.
Did I? mix up the whole thing.
Yes, sir, it's showing.
All right. So odds ratios are, like we mentioned initially, it was listed part of the tests of association. So this one is just the summary of the interpretation, not how it is calculated also. So the most important thing here is the last part on the interpretation. When you calculate odds ratio, it is going to give you a value. A value will be displayed. All you need to do is compare that value against 1. If the value is 1, if your odds ratio is 1, it means there is no association. That means that thing you are considering is what? Is not a risk factor. If the odds ratio is 1, it means there is no association. This one self that I picked is not the complete one, but no problem. Maybe you can I'll just explain so that so if the odds ratio is less than 1, anything less than 1, it means there is association and the association is a favorable one. That means that factor you are considering is even a protective factor. And if the odds ratio is more than 1, it means there is association. So these are the three scenario. It's either you see that the odds ratio is equal to 1, meaning that there is no association. That means no difference between what you are suspecting and the outcome. The frequency is the same. And if it is more than 1, it means there is what? There is association. So the higher the odds ratio, if the odds ratio, for example, let's say you are looking at the odds ratio for the association between cigarette smoking and lung cancer, and you get odds ratio of 3. So all it is telling you is that what? There is association between cigarette smoking and lung cancer, and that smokers are 3 times more at risk of developing lung cancer than non-smokers. If the odds ratio is 7, it is telling you that smokers are 7 times more at risk of developing lung cancer than non-smokers. So that is how it goes on and on. The value of the odds ratio gives you idea of the what? The magnitude. How many folds are they at risk? If it is 5, then they are 5 times at risk. So that is how odds ratio is interpreted. So if it is less than 1, on the other hand, because you can have odds ratios in as 0 point something, 0 0.3, 0 0.4, and so on and so forth. And we say if it is less than 1, it is what? Even though there is association, but it is more or less a protective association. Some explain it as an inverse association, meaning that one is going up, the other one is going down. For example, if you look at association between use of vaccine and development of disease, so it is likely going to, if that vaccine is effective, it is likely going to give you an odds ratio that is less than 1, meaning that those who use the vaccine are less likely to develop the disease. So that means there is association between using the vaccine and developing the disease. However, the association is a protective one, that those who use it are less likely. The other one, we say those who smoke are more likely because the odds ratio is more than 1. Here, the odds ratio is less than 1. For example, if you conduct a research to look at the association between using COVID-19 vaccine and developing COVID-19, and the odds ratio is, for example, 0.3. All you need to do is, in order to be able to interpret it well, so you can convert that odds ratio to a standard number. So just you can say 1 divided by 0.2, which is I think 5. So that means those who use the vaccine are 5 times to develop the disease. That is how odds ratio helps in interpreting whether of the association. If to likely to lead to the outcome you are, and then it is more likely. If it is equal to 1, look at this example. So you can see in this table, this is for logistics, is the result of a logistic regression that was done to look at factors that predict utilization of family planning. And 3 factors were considered: age, residence, and marital status. So you can see the column for odds ratio, that OR. For age, look at the odds ratio, 4. So it's telling us that those who are based on this result, and it corresponds to those under 25 years. So it's telling us that those who are less than 25 years old are 4 times more likely to use family planning. For those between 25 to 35, look at the odds ratio. The odds ratio is what? Is 2.3. So that means those who are between this age group are what? 2 times more likely to use family planning. And when you look at place of residence, urban versus rural, for those who are in urban area, because urban is considered compared with rural, for those who are in urban area, the odds ratio is 3.4. So here the interpretation is that those who live in the urban area are what? 3 times more likely to utilize family planning than those who are in the rural area. So that is how odds ratio is interpreted. But when you carry out regression analysis, it is not only the odds ratio that you look at. You look at the odds ratio, and then, because this is just an observation, it's just an observation, you have just drawn conclusion that yes, there is association between age and use of family planning. Those who are less than 25 years are 4 times more likely. But how sure are you? So that means this odds ratio alone cannot be interpreted. You have to marry it with the p-value. So when you look at the p-value for this observation, the p-value is 0.001, which is clearly less than 0.05. We said the cutoff is 0.05, and here we have a p-value of less 0.001. So that means this observation is what? Statistically significant. So that means there is statistically significant association between age and utilization of family planning. That means this observation that those who are less than 25 years old are 4 times more likely to use family planning is what? Is statistically significant. So this is when you use p-value. 95% confidence interval can also be used. The interpretation, I think there is a slide on how to use 95% confidence interval and interpret it. So here for 95% confidence interval, maybe I will reserve it when the slide comes, because confidence interval is a range that gives you with certain level of confidence where the actual value you are looking at, that is where the actual point estimate, because these are estimates. We have point estimate and we have interval estimate. So 95% confidence interval is a range that shows you where the true value is likely going to lie. So here we have odds ratio of 4. So all you need to do is what? Check this range 2.4 to 9.3. Does it include this value that is here, which is 4.02? If it includes the odds ratio, then that means it is likely going to be what? Statistically significant, because what we are looking for, you are 95% confident that it falls within this range. And when you look at it, you see that, oh, truly it is found within this range. So that is one thing to look at. Then the second thing to look at, there is what is called null value. Null value is the value that you conclude there is no association. So the null value for odds ratio is 1, because we said the interpretation of odds ratio of 1 is what? No association. So you look at this range also, this 2.4 to 9.3. Does it include 1? No. 1 is outside it, because even the lowest range starts from 2.4. So that means it does not include the null value. So once 95% confidence interval does not include null value, also it points toward the fact that yes, that observation is what? Statistically significant. But once the null value is included in the 95% confidence interval, it tells you that what? That thing you are looking, the observation is not statistically significant. So that means there are at least two things you need to consider when interpreting 95% confidence interval. First thing, that value you are looking for, is it included within the range? If it is there, plus. Then the second thing is the range. Does it include the null value? For odds ratio, we said the null value is 1. So does it include 1? If it does not include 1, then 2 pluses, then that means it is what? Statistically significant. So sometimes you can interpret your finding without even using the p-value. So if your calculation is correct, the p-value and the 95% confidence interval will all be speaking the same thing. So, but when we look at now between marital status and utilization of family planning, look at marital status, we said those who are married, look at the odds ratio, almost 2.75. But then look at the p-value. The p-value is 0.09. 0.09 is above 0.05. And we say anything from 0.05 and above is not statistically significant. So that means this observation that those who are married are about 3 times more likely to use it is not statistically significant. And if you look at the confidence interval also, it's from 0.23 to 5.3. 2.75 is found within the range. So yes, that one is tick. But when we look at the second consideration, the null value, this 0.23 to 5.3, that range includes 1, because it's 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, then 1.1 up to the 5.3. So that means 1 is included in the range. So that means because 1 is included, we conclude that it is what? Not statistically significant, because one of the requirements has not been met. We say for confidence interval, for something to be statistically significant based on confidence interval, at least 2 factors must be met. 1, that value must be found within the range of the confidence interval. 2, the range of the confidence interval should not include 1. So this one has included 1, and that is why it is not statistically significant. And if you look at the p-value also, is above 0.05. So that means all of them are speaking the same thing. So if you see that the two are speaking different things, go back to your calculation. That means something is wrong. You can't really interpret it. So this is the significance of p-value. I think no need to dwell on this. We have talked about it under chi-square. So the explanation is here. Confidence interval, yes, we just talked about it. We say is usually applied to mean, odds ratio, or relative risk. These are the three major areas that you apply confidence interval to. So we say it gives a range in which we can be fairly sure that the true value lies within. So example, if 95% confidence interval of a new antihypertensive drug reduces the blood pressure by 20 millimeters mercury, and the confidence interval is 13 to 25. So it means we can be 95% confident that the new drug reduces the blood pressure by 13 to 25. And when you look at this range, 13 to 25, it includes the 20 that that the new drug, the average blood, the new drug is cost. So in actual sense, all we are trying to look at in confidence interval is that value, if we say your mean is 3, you look at the confidence this thing has entangled. Well, we are almost there, that we call it a day. Please, are we back to this slide?
Yes, sir. Thank you.
All right. So we say we should what? Watch out if confidence interval does not include 1 for odds ratio or for relative risk, it is what? Significant. Once you check your confidence interval, what you are looking, your odds ratio is within the range, and that range does not include 1, then it means it is what? Significant. This is for odds ratio and relative risk. For mean, the null value is 0, not 1. Why we are saying for odds ratio and relative risk, the null value is 1, because the interpretation is once relative risk or odds ratio is equal to 1, we conclude there is no association. So if there is no association, then something cannot be significantly associated with a value. But for mean, if the confidence interval is for mean, the null value is 0. So that means we follow the same method. First of all, you check this confidence interval. Is your mean value found within the range? That is one. Secondly, now look, okay, the confidence interval. Does it, the confidence interval, does it include 0? If there is 0 in that range, then we say, it's not significant. But if 0 is not included, then you conclude it is significant. This one is for mean. For odds ratio, for odds ratio and relative risk, 1 is the null value. For mean, 0 is the null value. But the procedure of interpretation is the same. So correlation, here we talked about correlation. We say it is used to test association if the variables are quantitative in nature. So there are two major types. We have Pearson correlation. If the data is normally distributed, you use Pearson correlation. If it is not, you use Spearman correlation. The interpretation is still the same. So we are not looking at the calculation. all we are interested in here is what? The interpretation. Because when you use computer, it will calculate it for you, but you are the one that will interpret it. So the interpretation, correlation has a value. And that value, the result, ranges from -1 to +1. Whatever you are going to get in your calculation for correlation, that value must fall between -1 to +1. It can never go outside of this value. Anything more than 1 or less than -1 is not correlation coefficient. If it is manual calculation, please go through your calculation again. But if it is computer, of course, it will not give you a value outside this range. So the most important thing is, okay, how is the correlation? I mean, what will be the interpretation? So if the value is either 1 or -1, it means there is what? Perfect association. The association is perfect. If the value is 0, your interpretation should be what? There is no association. So that means the closer the value is to 1, the stronger the association. The same thing, the closer it is to -1, still the stronger the association. So if the value is a positive value, it tells you that the association is positive. That means it is a direct association. You have a positive correlation, meaning that if one variable increase, the other variable will also increase. If one variable decrease, the other variable will also decrease. That means the variables are what? Are moving in the same direction. So once you have variables moving in the same direction, it means there is positive correlation between them. If the value is negative, that means there is negative correlation. And here the association is what? Inverse. It means as one variable increase, the other variable will be what? Decreasing, and vice versa. So let's look at the various interpretations. Here also the no, I still need to, I don't know why is the wrong. Please just give me, because you also need the full interpretation of. If it is equal to 0, it means there is no association. If it is either +1 or -1, the association is what? Perfect. In real life, it is very rare to get a perfect association, but that is not to say it is not possible, but it's rare. If R is, the value ranges from 0, just above 0, up to what? 0.2. It tells you that it is what? Weak association. If it falls between 0.2 and 0.4, it means it's a what? Okay, the first one, very weak, and then the second, this 0.2 to 0.4 is what? Very weak correlation. If it is between 0.4 to 0.6, it is what? A moderate correlation. That means the association is moderate. Then if it is 0.6 to 0.8, it is what? Strong association. And 0.8 to less than 1, that means from that 0.8 to up to 0.99, it is what? A very strong association. So that is the interpretation. So, for example, if you are to look at this example, they say Adamu et al. Conducted a study to determine relationship between patients' systolic blood pressure and their BMI, and they reported a positive correlation between blood pressure and BMI, R equal to 0.651. So this shows that what? It is there is a strong positive association. Why? Because it falls, we said, correlation coefficient between 0.6 and 0.8. The interpretation is that what? It is strong. So that means if you do your analysis and you have something 0.65 or so, it means there is strong correlation between the variables you are considering. That means the association is strong. If, for example, what they got here was not 0.651, let's say they got 1 plus 1 as a correlation coefficient, it means there is what? Perfect association. If what they got was 0.12, that means the association is very weak, because we say from anything between 0 to 0.2 is what? Very weak association. And if it is exactly 0, we say there is what? There is no association. So let's look at comparing means. Also, sometimes we carry out research and we have several mean values, and we'll be required to test whether there is significant difference between the mean values or not. So sometimes the difference might be because we have carried out intervention. For example, let's say maybe you as a pediatrician, you carried out nutritional intervention on a group of children. After taking their weight, you realize that they are malnourished based on weight, and you give them intervention. And now you want to see whether the intervention is whether the intervention has worked or not. The way to do it will have been, of course, to take their weight before your intervention. You give them your intervention, whatever food supplement you want to give. After a period of time, you take another weight. So you compare the two weights to see whether they are comparable or not. So this is one example of when to compare means. So your objective, you might need to compare means or you might not need. So in any case, if you need to compare means, the statistical test to use is either a t-test or ANOVA. To see, t-test is used for comparing two means. Please, if you have two mean values, one to compare them, so we said single sample t-test, when you have sample mean, you have population mean, you want to compare them, you use single sample t-test. It is not among the ones that are commonly encountered, but sometimes you may need to use single sample t-test. For example, if you want to estimate, to know whether certain sample is chosen from a particular population, so you can use it. If you know the population mean, you can just compare the sample mean with that population. If truly it's chosen from that population, you expect the mean difference, you expect the mean to be comparable. That means you will not expect any significant difference in the mean. But if it's chosen from a different population, by the time you compare, you are likely going to see significant difference between the mean values. So this is one of the ways where this one is applied. But the ones that are commonly used are the paired t-test and the independent details.
Okay. Good afternoon, everyone. I just communicated with presenter Dr. Habibullah Adamu. He's still having network within. He's still having network issue. You couldn't join. I think the network today is terrible. So because hello, sorry,
We
my
cannot
network is
hear
also my
Okay.
network is also poor, so it has to log me out before I come back. So because of that, we're going to continue tomorrow, 4:30. We finish up the few slides that remain, then we do the question and answer session. I think, is it okay this way?
I think that is better,
So
so that
thank
at
you
least we'll
so
still
much.
get it better.
Yes, yes. So we are going to continue tomorrow, 4:30. Thank you so much for your participation. Thank you so much for the understanding. Thank you. I wish you a nice day ahead. Thank you.
Mohammed.
Thank you, Chief Amaru.
Thank you, Dr. Amiru. The time is 4:30 tomorrow. Somebody was asking in the chat box.